Okay, and this is the main thing here, the gas lift data or gas lift parameters. Okay, you can click on this add row. Okay, and then you input the MD, the location of the gas lift valve inside the production string, the measured depth, the true vertical depth, temperature at that location, and manufacturer. You can select the manufacturer of the gas lift, the model. So we have, quite extensive library here. And you need also to provide the port size, and then R will be automatically imputed. And then TRO, test rack opening pressure, the correlation that you will use. Currently, there's only Thorn and Carvenhill, and the type of the well. Okay, it is also, will be manually or automatically imputed. Okay, so for simplicity, I will skip the, the gas lift valve detail design. Here, right away, I will go directly down to setting the location for my orifice valve. So orifice valve will always, will always be open. It's an orifice, so it's not like normal gas lift valve where you will have throttling operation, close and open. Here it's an orifice. Okay, and usually we use orifice at the, at the deepest position of the gas lift settings, gas lift string configuration. This is the valve, the gas lift valve that is located at the bottom, at the lowest location, and thus this is usually the operating valve actually. All right, so I use gas lift valve. Let's say I name it gas lift or GLV or GLV. This is the location for the measured depth, 3,250. I input the TVD, the temperature, and let's say the manufacturer is Chemco. The model is RDO. Okay. All right, and then the port size is 16 inches per 64 inches. And the R is 0, TRO, let's say 0, Thorn-Cravenhill for the correlation, and of course the type is an orifice. Okay, and then you need also to input the gas lift input parameters, the operating pressure when the well is producing continuously at stable operation by gas lift, injection gas gravity, let's say 0.7, the same with, reservoir gas. So you just circulate or recirculate the gas from the reservoir, and then you will use it as gas lift valve. So injection gas gravity will be the same. And valve differential pressure for stable injection, stable, operation, we set the valve differential pressure of 100 between the upstream valve and the downstream valve inside the tubing. Gas injection rate, let's say 0.5 mmCFD, and the input here is the gas injection rate, but you can also switch it to GLR. Okay, the resulting GLR if you already inject the gas. Okay, but let's use 0.5 here, gas injection rate. I think it's simpler. All right, and then so we get the dashboard. Here you can see the symbol, the picture for the gas lift. And let's go directly to analysis. So as usual, nodal analysis mode, operating point. We check on the stability checked. And for gas injection depth, let's select deepest injection point, because usually the deepest injection point will give you the highest production rate. Okay, this is the most efficient placement for the gas lift itself. And we tick on this use existing active mandrel. Okay, with the maximum depth of gas injection, we select use existing active mandrels, which is 3250 measured depth, just like what we input in configuration. All right, and then here for the calculation node, okay, the outlet node, the wellhead pressure, let's say switch it to PSIG 140, okay. It will be dependent on the system pressure, the facility pressure, and the bottom node, of course, in reservoir depth, the solution node at the bottom hole or at the casing depth. Okay, so let's just click on calculate, and very simple, we get the flow curves here. So at this parameter, or at this, at this setting, we get the, FBHP, the flowing bottom hole pressure of 332. We get the liquid rate of 96.5 stock barrel per day. So we get the good 43 stock tank barrel per day of oil. This is the water, this is the formation gas, and this is the injection gas rate. So you see here we have 0.5, just like we set on the design, 0.5 mmSCFD. This is the water cut, so the produced GOR is this. This is the location for the gas lift injection or the orifice valve, stable injection, stable production, stable operation. And we can also depict, or we can also present the wellbore equipment here. This is for the temperature, all right? Sorry, this is the casing pressure or gas injection pressure, okay? Starting from, you can see here the value. It's 564.7 PSIA or 550 PSIG, just like what we inputted here. 550 PSI or PSIG. If you change it to PSIA, it's this value, which is exactly the value we have at the top here. And then this is, of course, the temperature profile. This is the production profile. Okay, you can see a change of gradient after you inject the gas. So the change in, the gradient occurs right at the location of the orifice. So the gas will be mixed, all right, with the production fluid, the gas will bubble up, and of course it will lighten up the production or the producing fluid gradient, and then you get this profile. Operating rate versus water cut, okay, still blank. Operating rate versus operating pressure versus water cut, still blank. Gas lift diagnosis plot, okay. And I think that's all. The rest are report analysis. But the main thing for us right now is still the nodal analysis. Okay, so we already design the gas lift, we input the configuration for the orifice valve, the location, the size, the correlation that you use, you input it here, and then you run just like usual. In WellFlo, you create the nodal analysis and you get the result. Okay, hopefully in the future we can also set, or we can also design the complete gas lift from the, the loading valve, like at the top and then at the middle, and lastly at the bottom you set the orifice valve. But I think here we can stop it here. We can call it a day. So thank you so much for watching. I hope this video is useful. I hope this video is important and helpful for all of us. Again, thank you so much for watching. See you again in the next WellFlow videos. Thank you.